So let's start. Dear colleagues, good afternoon or good morning. It depends on what time right now at your country. First of all, on behalf of our various speakers and participants, I would like to thank you, Adivola Desin from FERAL, from Forum of European Research Laboratories, Highway Research Laboratories, and to Kostas Bouklas from Institute of Communication and Computer Science from Greece for supporting our initiative, the Netivei Israel initiative. The team that was actually initiated this talk and after that this event was Tamir Agiv, who is responsible for resilience and disaster management in our company. Also, Itzhak Ashko, who is a section manager for international relations and knowledge management, and Avi Bachar, who is actually an engineer and chief tunnel scientist in our company, and also all other who actually invested time in preparation and presentation and so on. It is very important for us to meet a team of resist researchers with a community of Israeli researchers and users and stockholders. Special thanks to Dr. Karen Philbrick from Mineta Transportation Institute for accepting the invitation of Mata from Disto to join us as a keynote speaker. Also, choosing this as a date of the workshop, we had no purpose to compete with president elections in USA. So good luck with the elections. And also thank to all the speakers for the effort and time investment making this event happen. This event, despite of both COVID-19 pandemic and recent lockdowns in our countries. And before we start an official part, I would like everybody switch on cameras. We will try to make a picture. It is a special request from Angelica, who is a dissemination manager for
I will send you a selfie offline.
offline.
You can add it.
Yeah, Costa, because of your electricity issues, please send us your selfie. I will put inside of this photo. Okay, just a second. I will make something. Angelica, can you do a picture right now?
Yes.
Please do. And
yes.
Is it okay?
Yes, probably. Just a second. Once more. 1, 2, 3. Thanks.
Wonderful. Thank you. Thank you so much. Okay, wonderful. So let's go forward. So now I would like to invite Mrs. Revital Levy to open the workshop with welcoming remarks. Revital has recently joined the Netivei Israel team as the R&D department manager. She brought us a really positive energy and experience of 25 years in design and engineering of complex systems. Revital, your screen and your turn, please.
Thank you, Costa. Thank you, Edward, for the opportunity to open the event and to join the team of Resist developers. My name is Revital Levy. I'm the head of the R&D department in Netivei Israel. Although I may be new in the field of transportation, I am a veteran in the field of engineering and the R&D. I have a Bachelor of Science degree in aeronautical engineering and Master's of Engineering degree in system engineering. And in the last 25 years, I had the privilege to work in some of the most challenging, cutting-edge system of systems projects in Israel, taking part of different development stages from early system requirement definition through preliminary and detailed design and up to verification and validation. And now I am honored to be a part of the team responsible for the future of the Israel transportation infrastructure. A few words about Netivei Israel. Netivei Israel is a fully government-owned company that was established 100 years ago, even before the founding of the State of Israel. And it is the largest transportation infrastructure company in Israel. Netivei Israel is a multimodal company. We are in charge of the design, construction, and the maintenance of interurban roads, in charge of traffic management and the safety of the road users. And we're also in charge of the design and construction of all new railroads in the country, and has recently been assigned the responsibilities for the design and construction of the new international airport of Israel, supplementary to the Tel Aviv International Airport. Our company acts as both a transportation infrastructure authority and as an innovation and R&D national hub. The R&D department is the core part of the strategy and the innovation division that was established in Netivei Israel in the beginning of this year in order to exploit the various opportunities that come as a result of advanced technologies and innovative ideas, which can change the world of transportation in the 21st century. And of course, alongside the advanced technologies and the innovative ideas, there are significant economic, social, and environmental challenges that all require some perceptual changes and of course require R&D toward more sustainable transportation and toward a safer and improve the resilience to extreme events, both natural and man-made. The R&D department leads a roadmap for utilization of this design, construction, and maintenance of roads. And that, of course, includes the improvement of road safety and the resilience to transportation infrastructure. And another core topic of the R&D is advanced solutions for traffic management. All that laying the groundwork for the era of autonomous vehicles and semi-autonomous and connected and cooperative vehicles. For that, in order to do that, we initiate pilots and collaborate with a variety of organizations, startup companies, technological companies, construction companies, and research institutes in Israel in order to come up with practical solutions to existing problems and promote innovative ventures. And now I'm happy to open this meeting, welcome all the participants. We here at Netivei Israel believe that the Resist project will improve the road authorities' capabilities to address natural and man-made hazards and extreme infrastructure damages. We are sure that this advanced technologies applied by the Resist project will provide capabilities and measures for assessment of road infrastructure vulnerability and traffic management at extreme events. All that with the outcome of improved road users' safety. I wish us all a productive meeting and productive discussion, benefit of all sides. Thank you. Edward, please.
Thank you, Revital. Resist is standing for Resilient Transport Infrastructure to Extreme Events. The project aims to increase the resilience of seamless transport operation to extreme events, protecting the users of the Europe transport infrastructure, and providing optimal information to the operators and users of the transport infrastructure. It is concrete challenge in need also in Israel and USA for this kind of project and solution. I would like to invite our keynote speaker, Dr. Karen Philbrick, who will speak about resilience of the transportation sector and driver safety in the USA. Karen, please, your screen,
Thank you.
Microphone.
Yes, I think my microphone is on. Can you hear me okay? Excellent, thank you. And I'm watching the time here because I know our agenda is tight. Like Edward said, I'm Dr. Karen Philbrick, and I have the pleasure of serving as the Executive Director for the Mineta Transportation Institute at San Jose State University. We're located in the heart of Silicon Valley, right in San Jose, California. And as mentioned, today is a big day for us with the election, and certainly infrastructure being one of the key topics in this election. At the Mineta Transportation Institute, we do surface transportation research, technology transfer, education, and workforce development. We oversee a national consortium of university partners, have about 150 research projects in process. Most importantly, for the topic here today, we run the National Transportation Security Center, which receives funding from the Department of Homeland Security to maintain a global database on terrorist activity against surface transportation targets. But the bulk of my comments today will focus on 4 separate areas. But before I jump in, please forgive me if I need to take a sip of coffee here or there. I joined you before 4 a.m. today, and I know we're all hailing from around the globe. So thank you again for the kind invitation. Now, as you may know, the U.S. Cybersecurity and Infrastructure Agency has identified 16 critical infrastructures in the United States. These assets, systems, and networks, whether physical or virtual, if they are disrupted, their incapacitation or destruction will have a debilitating effect on our security, our national economic outlook, our public health, and our safety. And in the United States, much like around the globe, we are reminded right now through COVID-19 and other experiences that transportation is one of those critical infrastructures. We have numerous natural disasters such as wildfires. COVID-19 has dramatically impacted the transport of people and goods in our nation. And although there are many definitions of resilience, I'd like to briefly talk about 4 areas today. That's public health and infectious diseases, climate change and natural disaster, cybersecurity, as well as terrorism. Now, each of these are critical to ensuring safety, seamless connectivity, economic growth, and continuity of operations. But let's start with public health and infectious diseases. Here in the United States, we in large part remain on lockdown on our western states. Today, as of this morning, public transportation ridership remains down 65% nationwide. And in the Bay Area specifically, that figure is closer to 88%. What we're seeing is about 92% of our riders are not choice riders. These are people who do not own their own automobiles and must use public transit to get to their places of employment. In large part, these are our essential workers. And while there's much research being done to identify the spread of infectious disease on mass transportation, the results are inconclusive. And from a research perspective, it's very difficult to determine if someone gets COVID from an airplane trip or a public transport trip. So for a variety of health and other reasons, the US is behind much of the world in implementing effective contact tracing and helping to understand the issue pardon me, of how COVID is impacting our transport sector. Now, the American Public Transportation Association, better known as APTA, conducted a study that looked at how people feel about riding public transit. If there are any COVID clusters defined as 3 or more cases that come from a specific light rail, bus, or other transit network. And what we're finding in the US, and you've likely seen these results replicated in Austria, France, Japan, and others, is we're not seeing those clusters emerging. Rather, they're coming from larger gatherings, places of worship, hospitals, and other points of contact. So here in the US, our focus right now is getting people back to moving and feeling safe rather than viewing transport through a lens of contamination. Now, what is clear is that layers of protection is needed to slow the spread, and both airlines and our transit agencies are installing hand sanitizing station, plexiglass barriers for our operators, and in some cases for our passengers. We're employing social distancing, filtration systems, and electrostatic spray disinfectant. Other strategies are being employed globally, and we're looking to best practices and lessons learned, but we are still very much in the throes of this pandemic and are suffering its outcomes. But that's not the only challenge we have right now in the United States. We're also looking at climate change and natural disasters, which both have a notable impact on the resiliency of our network. So first and foremost, our transportation systems provide critical, and I mean critical, lifelines during disasters. Not only do they bring first responders to the scene of an incident, but they deliver critical supplies, facilitate evacuations. What we saw after 9/11, for example, is a number of people were evacuated by subway operators, people who continued to operate those trains and those buses to help people get to safety. This year alone in the US, there have been nearly 34,000 wildfires, which burned approximately 2.3 million acres. These events have caused tens of thousands of evacuations, and a number of our states have responded to these disasters and extreme weather events by incorporating evacuations into transportation planning. In many parts of the US, the most common form of evacuation is the personal automobile. And certainly in this wildfire season, that's made even more challenging with COVID. We're seeing that even more. However, it is not uncommon for buses and trains and planes to aid in evacuations. One example from one of our states can be found in Florida. They implemented contraflow scenarios so that they can alter traffic on freeways to aid in emergency evacuation. Similarly, there's a program launched that looks at an emergency shoulder use plan to expand capacity, and similar strategies are being employed in numerous states. Mostly we're seeing this in the southern US. Incorporating risk assessment methods to ensure that our assets remain in a state of good repair is critical to resiliency. In the US right now, we face billions and billions of dollars worth of backlogs because we haven't kept up with our infrastructure, which from the American Society of Civil Engineers receives a grade of about a D. So I don't know about you, but if my child came home with a D, I would not be very pleased. And so right now in California, for example, we've passed Senate Bill 1, which will yield about $5 billion annually for a state of good repair focus on our transportation system. Also includes funding for active transportation, emergency management, as well as public transportation. And that leads us to the third topic, which is cybersecurity. And Edward, I've got my eye on the clock here. No conversation about resilience would be complete without touching on the importance of cybersecurity to the safe operation of our systems. Now, while a number of programs have been implemented in the US, a recent report shows that only 60%, that's 60% of our transit agencies have a cybersecurity preparedness plan. In order to safeguard against such breaches, this sector must understand how to mitigate and respond to growing threats. This becomes even more important when autonomous vehicles, our grid, becomes instrumental to the operations of our transportation systems, our trains, our automobiles. We also have to pay more closely attention to this right now because so many people are working from home, which opens up another challenge. People might leave their computers unattended. They might have children. They might respond to phishing ware. These are all breaches that could lead to cybersecurity problems. Think about positive train control. What would happen if there was a breach there and a bad actor became in control of that particular train? Then imagine if it was transporting hazardous materials. We need to do a better job in the US of providing funding and paying attention to that particular threat. And now on to terrorism. Since 9/11, I think you all know the US has implemented a multitude of strategies focused on enhancing security, preventing terrorist attacks, and also responding to man-made disasters. Yet in spite of these developments, in the US, unfortunately, we remain vulnerable in a number of areas. So while there's been lots of focus on the aviation sector, that same benefit has not been applied to the public transportation sector. Across the entire passenger and cargo ecosystem, more work is needed to develop and deploy effective biometric capabilities for travelers and transportation workers, improving risk-based approaches for vetting and screening passengers and workers, certainly developing cost-effective solutions to screen freight and public transit passengers without causing undue delay or disruption. And finally, enhancing coordination among our many different agencies and levels of government to effectively detour and respond to both terrorist and man-made disasters. And I do see that I've been going for 11 minutes, so I'm gonna wrap up here, understanding that we could talk about this for the better part of a half a day. But I will end on this note, which is even though we have numerous innovative and emerging technologies on the horizon, such as automated vehicles, the US continues to underinvest in physical and cybersecurity, which could have dire consequences. And that's even more of a reason that these international partnerships are so critically important, so that we can share challenges, opportunities, and best practices without necessarily duplicating our research efforts. I'll close by simply saying thank you. I hope the opportunity to actually engage with you at a future workshop and in person presents itself. And I'll stop there with an invitation that you contact me at any time if I can provide further details or research resources. Thank you.
Thank you very much, Karen. Impressive and really challenges that the USA facing right now in the transportation sector. It's quite common around the world. Of course, sustainable development, safety is the first, health, and the employment of advanced technologies like automotive and so on. It's quite big challenge. To all the participants, I would like to remind you that the questions you can write down as via chat or Q&A section, and we will discuss all the questions and give replies during the session of questions and answers. Thank you very much in advance. And the next speaker is Kostas, actually a Resist project manager. Will give an overview of Resist project and its recent developments. Kostas, please.
I don't know if you can see my screen. You can. All right. All right, thank you very much. First of all, I want to thank everybody in the Resist Consortium for helping out with this event. It wouldn't be possible without everybody's help. And a special thank you to Dr. Philbrick, and be certain that we will gonna call up on your invitation for further cooperation. I will try for the next 10 minutes to give some highlights on the Resist project, like a general overview, in order to have a more general view of the project, since it's quite extensive and it would be extremely difficult to give every detail of the project in 2 hours. Actually, if I let Guillermo and Miguel talk, they will take about 4 hours just for their own part. So we are a consortium of 17 partners with 2 infrastructure users spreading across Europe, and of course our 2 partners in Israel that I'm going to give a special mention since they're the event, Native A, that is working with FERL, and Ben Gurion University that is working with us in our mobility continuity work package that we will be discussing later in the day. We'll talk about some concepts, the concept and some objectives already mentioned by Dr. Philbrick, that we have done a great achievement in the field of transportation, critical structures like bridges and tunnels, which that are still susceptible to extreme events, either that being natural or physical or man-made, voluntary or involuntary. And in today's world that everything is connected through IT, we have to consider cyber attacks as well. So the Resist project had some major concerns that it needs to look after. It needs to protect users and ensure seamless mobility in order to avoid any kind of human and financial cost, to prevent, predict, and increase resilience by monitoring vulnerability and offering predictive analysis, and moving forward to that, risk monitoring and assessment of the structures that we are that we are handling, and of course to react and provide the optimal information in order to minimize any kind of impact that happens at an extreme events, and try to restore services in an optimal time. The project focus is, this is a graph that I really like that I took from Dr. Kruger from Bast Institute. It's not mine. We're working through the whole resilience cycle except of maintenance. We don't do any maintenance work, we do monitoring. So the project architecture that will give you a better overview of the project as a whole. So we have our infrastructure that being bridges, and we're looking into bridges and tunnels predominantly. We have a number of systems that are going to be using. Mostly the inspection is going to be happening through drones. One of the objectives is to be able to mount sensors using drones, which is one of the like a really innovative things that we're trying to do. We're going to be using laser systems in order to do measurements and provide the locations of to the drones. The whole idea is that the periodic collection of data, the way that's happening now using human personnel, is quite costly, it's time consuming, and in cases of extreme events, it can be very dangerous to the worker's life. Actually, in case of an extreme event, then the structure can be inaccessible by humans. So the remotely piloted aircraft, except of the mounting of the new sensors that I already mentioned, it will collect data from sensors attached on the drone, like 2D and 3D images of the structures. We're going to be handling with secure data communications by using the picture below here, the RedCom node that has the capability of taking over the whole communication cycle of on an area, especially when in a case that some kind of event has taken out the communication network. It has the capabilities of satellite communication as long as many other communication lines like Wi-Fi, LTE, and any other state-of-the-art communication system. Situation awareness and decision, we're going to be using, as I said, sensors, images, photogrammetry, vulnerability assessment models, psychological and behavioral factors that are being researched by Ben Kuriat, and with a sentiment analysis that it's being researched by ICCS. Strategies for mobility continuity we have created a rerouting system using multimodal strategies, and strategies for risk assessment and management that will give the state and future state of a structure. And in real time, we're hoping that we will be able to give an awareness of the situation, require actions to minimize the impact, and propose final proposed measures to increase the resilience in the future. Okay, our mobile app, I'm going to talk about it later. We have created a mobile app for continuous communication. What it actually does is that it disseminates information about the event to the users of a highway leading to a structure that has been damaged. And adding to that, it will be able to give rerouting information, either dynamically or static, meaning that for some countries, for example, in Greece and Italy, you can't dynamically give a new route. You have to use the one that the civil protection has proposed, but the system is built in order to be able to give dynamic rerouting as well. Some innovations that we are creating within the project: aerial robots for inspection and mounting of sensors, as already said, ultrasonic sensors suitable for the air pass, computer vision systems for the air pass, secure and resilient communication systems. I haven't talked about it, but the whole system is protected by a holistic cybersecurity platform that covers both the infrastructure of the end user, meaning data centers, etc., but the field operations as well, meaning any kind of field device that we're using in order to measure, as well as the drone. And that went to number 5. That was the cross-layer cybersecurity solutions. The mobility continuity for passengers and freight. I should have mentioned in this one that it's multimodal. It will be able to give suggestions for different modes of transportation, risk assessment and management for extreme events, and of course everything is integrated in one Resist platform. The validation will take place in real conditions and in real infrastructures. Of course, when we started the project, we didn't know that we will be handling a real life global extreme scenario. But when we are allowed to, we will be checking our system in Bridge T9 in Greece. It's quite a large structure. We already have surveyed it, and we will be running all the scenarios on this bridge. And then, except of the GPS denied environment for the drone, that it will be run in the San Petronila tunnel in Italy, as well simulations of the test that we already ran in the bridge in Italy. We will be running it in the Millers viaduct in Italy as well. I wish I could tell you when that's going to happen, but because of COVID right now, I can't. Finally, I want to invite everybody on another workshop that we're making. It's based on resilience and all the projects that were in the same call as Resist, meaning Forces, Safeway, and Panoptis are taking place. It's going to be a very interesting discussion. You can find the workshop through Resist project, and we would love to have everybody there in order to see the different approaches for every project on the call. And that's about it. I did 8 minutes and 30 seconds, and I'm going to give it to whoever is next.
Okay, fine. Kostas, thank you very much. Yeah, it's really ambitious plans for testing in a view of recently lockdowns and so on. But I suppose the stuff will be actually corrected in the nearest future, and trials will be done. I also maybe hope that Native Israel somehow will attend and grant from input from our knowledge to the trials. The next speaker, who will actually our partners from Spain, and in 2016 visiting University of Seville and Father Fadek laboratory. I was impressed by creativity and engineering solutions for award-winning project Aerobi, actually which developed the UAV with robotic arm for bridge inspections. Right now, I would like to invite to talk about further developments and applications for Resist project, Professor Guillermo Herrera from University of Seville, and Dr. Miguel Angel Trujillo Soto from Father Fadek. I hope I pronounce, Miguel, your name is correct. So
more or less.
more or less. Sorry, my Spanish is not so good. I have to improve it.
Okay. Can you see the presentation?
Yes.
Okay. So yes. So thank you for the introduction, Edward. So this Miguel Angel and myself will jointly present this section. That the idea is to just to present a high-level description of the robotic system or robotic actors that we are developing in the Resist project. Okay. The idea of the robotic system is it's a flying robotic system that, as Kostas has mentioned, the idea is that these robots will carry the inspection sensors that, for example, the cameras for visual inspection, and also ultrasonic sensors and other sensors for contact inspection. So from the experience from previous project, and specifically from Aerobi, so we ended making a design of a robotic system, not only one robot that can carry all the all the sensors because it will be very large, very heavy, and also not very practical. So we got the solution of a robotic system composed of different robots with different tasks. So mainly an aerial robot that it is made for the visual inspection, that it will be always needed for bridges and tunnels. And then another aerial robot for contact inspection. So for inspection with sensors that need contact. For example, the sonic sensor that you will see in the next section. Okay. So Miguel Angel, if you want to.
Yeah. So regarding the visual inspection robots, this one is the one that we are going to use for both use cases, both scenarios, that are the bridges and the tunnels. And this robot is based on a commercial drone with multiple adaptations that we perform here in CATEC. Okay, we add, for example, propellers protection, a gimbal on top of the drone with vibration dampers and so on. So more or less some, let's say, more standard things, but we also added this LiDAR for localization under the bridge where we don't have a GNSS coverage. And also inside the tunnel, that of course we don't have that as well. Maybe Guillermo, you can go to the next slide. So as you can see there, we have been testing the robot with a LiDAR flying indoors where we don't have this GNSS coverage. We have this onboard PC for this custom flight control. And also we are using a commercial autopilot where we interact with this autopilot using an SDK interface and so on. So we have been testing this first prototype that has been already built, as you can see. The first test here, as you can see in the indoor test, we have been performed. Currently, we are finishing the integration of on the stereo camera that you will see later, that my colleague will explain. And we're also performing the first flights outdoors in real conditions with wind and so on in similar scenarios like bridges that we have close by here in Seville. Next slide. So we also have, as Guillermo was saying, contact inspection robots. And this one, the one that you can see in the picture, is a previous version of a robot that we developed for bridges. And we use this one in Nairobi, as Edward was saying. And this one has a very special capability. That this kind of robots, this kind of robot that we develop here in CATEC, they have the capabilities of touching the surfaces. Okay, so being touched with any surface, let's say vertical, horizontal, or whatever that the bridge can have, but while we are flying. Okay, and this is very important because the sensors that we want to use here in the project must be in contact, most of them. For the visual inspection, of course, we are using a camera, but for when we have to measure, for example, a crack depth, for example, so we need to be in contact. And also my colleagues will explain later several of these sensors that must be in contact. So we took this technological base of CATEC and we developed a new robot, okay, with less weight, because we know that this is important for an user, and this one is going to be more powerful, so we have more payload in the robot, and we are introducing several changes in the way that this robotic arm that allows us to be in contact with the surface. So in order that the operation is safer and also faster. And next slide, please, Guillermo. So we also include propellers protection that we didn't have in the past, and this is why we know that this is important as we are flying very, very close to the surfaces. Okay, and we also include this cover in order that in case we have some little rain and so on, so we are covering electronics and so on. And of course, several redesigns, testing cycles have been performed. As you can see there in the video on the corner on the right, so you can see the robot that is flying, touching a surface, and also the surface is changing its curvature. And the way this is possible is because we have several sensors on the robotic arm that allows us to follow, let's say, this car that you see touching the surface. So in this way, the drone is fully autonomous, following let's say, the desires of the operator. Okay, so the inspector is actually the one that is moving this car that is moving along the surface, and actually the drone operator is doing nothing. Okay, because this operation is fully autonomous, and the drone is in fully automatic mode, following the place where the inspector wants to go. Okay. And as you can see, we have been testing this indoors, and currently we are doing our first test outdoors. Next.
Okay. Also for the for the tunnels, for the contact inspection of the tunnels, we decided to have a different robot because of the inside the tunnel. So the space is less, so you have a more confined space. So we need a smaller robot that is able to just move inside the tunnel without many restrictions. Okay? So we have the precedent that you can see here in the photo in the middle, that this comes from the Aerobi project. This was small aerial robot that is able to stick to the surface of the tunnel. You can see here on the lower part of the beam, of a beam. In this case, what we use is we use it to measure the deflection of the beams, while from the ground with a total station we will be automatically follow a prism, reflector prism mounted on it. And we also have a first prototype. You can see here the FAIR, the fully actuated inspection robot. Just to have insights on how we can design, how we can finish the design of this aerial robot. From the experience of all of these previous robots, and also taking into account that in this project, so one of the sensors that we need to use is the one that you see here. This is a radiometric sensor. It's a prophoscope that is a sensor that is used to measure the cover of the rebar. So it can measure the position of the rebars, and also the cover, the width of the cover that is on top of the rebar. But so the usual way of using is just you have to touch with the sensor the surface of the concrete, reinforced concrete surface, and then slide in one direction and take measurements at the same time. So for this, just taking into account this, we designed a robot that this, you can see here is a compact multi-rotor with 8 rotors, but with a manipulator that is that is at the end, this manipulator is able to rotate around the base of the frame of the multirotor, just to adapt to the different inclinations of the surface of the tunnel. And in the manipulator, we have something like a 2D manipulator, Cartesian manipulator. So we will mount the sensor here in the center part, and we can move it around, just following any trajectory in the 2D space. So with that, we have a lot of flexibility, and just to use this sensor, and also another ones that not need precise positioning. So for this, so we are building right now the final prototype of this. We have developed the manipulator, and we have mounted it and tested it, and also the platform. But we will, in the next month, we will have the working prototype of this. And also for all the robots, there are some functionalities, we call the autonomous functionalities, that are very, very important, because we are working in a place that are confined space. We will not have access to the satellite signals, so we will not be able to use the GPS or GNSS sensors to get the global localization. So what we will use is a combination of onboard and ground-based sensors, sensors that are mounted on the drone. Some of them have been explained by Miguel Angel before. This 3D laser, and also these tracking cameras, and also, of course, boards, inertial sensors, and so on. And also we will have the total station that will be on the ground. And it is also used to measure deflection of the beams and inclination of piers. We will use these measurements also jointly with the others to get a very precise estimation, because it is needed. So the idea is that we will use the robots from one side to locate the defects on the surface of the bridge or the tunnel, with a process that will be explained in the next section. But we need very high accuracy in the localization, in order for the other robots just to go there and make the contact inspection, and also just to localize them, so that in another inspection that we will do 6 months later or 1 year later, we will be able to localize precisely these defects and see the evolution and so on. So we have develop an online localization system in real time that we can use for navigation, and also the inspection with the ultrasonic sensor and the radiometric sensor, but also an offline localization system with that will be done after the flight, with post-processing, using and to get a higher accuracy localization of the defects on the images. And also we're using several sensors, depth cameras, for collision avoidance in the navigation. Okay. Well, there are more details on the on the localization systems. So I think that the real-time localization system, we will use several combination of systems, or using the total station and the tracking camera, and also the 3D LiDAR, and a previous map, and tracking cameras. We are making tests with both approaches. And the offline localization, we will use photogrammetry to reconstruct the bridge, and then take get more accurate localization of the defects. Okay. So for the control of the robots, just a few a few words. So this is very important that this is also always that you have a robot, an aerial robot, that you have to fly very close to any object or the surface of the bridge or the tunnel. The controller has to be much more precise. So you have to take into account also the aerodynamic effects or the rotors that are just recirculating the air near the bridge or near the tunnel walls. And also the contact force, because whenever you touch the surface, that you will get a reaction force that can instabilize the aerial robot. So we have to get all this into account. Okay, so next, Miguel Angel.
So regarding the ground control station development, so as you can imagine, of course, we need to control everything that is happening on the drone. Okay? And we have two main modules for this, and one is the mission control, and let's say is where the operator is seated on a table with a computer in front, and there you can see there the drone path, the engineering interface where you have all the information of the drone, of its status, on all the, so everything, you can access everything on the drone from there, and also you can operate the sensors and so on. And also we have the, let's say, the pilot interface, that is totally different thing, that is, let's say, more based on a situational awareness, cameras. So in order that the pilot is receiving all the really, really important information as fast as possible, and in a very concise way, in order to take the better decision if this pilot has to take manual control of the drone. Because let me remind you that, of course, we need, based on the current regulation, we need this pilot right now, okay? Even if the operation is highly autonomous and the pilot most of the time is not doing anything, but you need to have him anyway. So in this way, you have this pilot in order to for safety, no? In order to take manual control if something is happening. Next slide, please. And this ground control station for the pilot is something similar of what you can see on the right, on the picture on the right. So as the drone is flying fully autonomously, we consider that the pilot needs to have these onboard cameras of where the pilot, where the drone is heading to, and also a camera on the corner, on the left bottom corner, that is where the drone is taking pictures of. And also you can see all around the screen that there are some, let's say, indicators that is showing the pilot how far are the obstacles, in what direction, and what are the intentions of the drone at every time. Okay? And of course, this must be executed in a laptop for easy transportation, deployed in very short time, and of course we have friendly interface. And this, and let's say the summary of this interface is very simple but powerful at the same time. Next slide. And yeah, this is just to show that we are testing right now because of COVID, no? In the, not on the real environment, but just some testings of the video and interface. Next slide. Yeah, and this is the end, so thank you very much. And if you have any question.
Thank you a lot. I just write down that the questions can be submitted to through chat or Q&A section, and we will address them during the discussion session. Thank you very much, Miguel and Guillermo, for introducing your developments. I just would like to highlight that these developments got Innovation Radon Prize in EU in 2017, right?
Yeah, right. The inspection robot will obtain this Innovation Radar Prize from the European Commission for that development.
Yeah, together with Professor Emeritus Aníbal Olero, right? I hope I pronounce your names correctly.
Yeah.
Thanks a lot. The next speakers represents leading research institutes in Europe. I would like to invite Dr. Luca Belsito from Bologna Unit of National Research Council of Italy, Institute of Microelectronics and Microsystems, who's responsible for development of ultrasonic sensing unit. You can correct me if I'm defined it not exactly as the engineers like. And the second one, he will give a presentation together with Professor Ramesh Viswanathan from Goethe University Frankfurt, who is responsible for image processing and visualization applications. Gentlemen, please, your screen and microphones.
Yes, can you see the screen?
Yeah.
Okay, perfect. So in the first part of this presentation, I'm going to introduce the contact measurement. Instead, in the second part, my colleague will describe the vision suite. So basically, for the contact measurement, what we want to realize, we want to take crack depth measurement and also crack width measurement for structural monitoring. At the same time, we want also to attach a vibration measurement module to take acceleration measurement. So here in this slide, we can see that on the top, the crack depth measurement. Basically, we use two piezoelectric transducers, one on the left, one on the right of the crack, and together with a pulse receiver unit. So when with this generator we have an ultrasonic wave, this propagates across the concrete, is reflected from the bottom of the crack, and then is detected by the receiver. If we measure the time of flight, basically the time between the generation and the detection, we can measure the depth of the crack. Basically, by exploiting the Pythagorean theorem, we are assuming to know the ultrasonic speed. With the same principle, we take also the ultrasonic speed measurement in a region really close to the crack. For the crack width measurement, instead, we use the completely different sensors. This here that you can see is an optoacoustic receiver. It's an array of sensors together with the piezoelectric transducers. I will describe better this later. We have found in the market several pulse receiver units, but they are too big for this kind of integration on the drone. And especially when they are small, they don't have the right specification, because for a crack depth measurement, it's really important to have an actuation voltage of at least several kilovolts. So we design to design this custom pulse receiver unit here on the left. This is really flexible, so it's able to generate driving voltage up to 3000 volts, and it's able to measure the time of flight with really high precision with 55 picosecond time to digital converter. The dimension of this custom pulse receiver unit is very small. It's 12 for 5 centimeter, and the weight is just 90 grams. So can be easily integrated on the end effector of the drone. On the right, we can see an example of ultrasonic wave detected by using this custom electronic during a crack depth measurement performed on a concrete sample by using two 54 kilohertz piezoelectric transducers. For the width measurement, we use this optoacoustic receiver here. It's an array of several sensors together with the piezoelectric generator. We generate an ultrasonic wave here that propagates across the concrete, and then is detected by only the pixels on the sensors that are in contact with the concrete. Instead, the pixels here that are on the crack cannot detect ultrasonic waves. So by comparing the signal acquired in the two different cases, by the pixel on the concrete and by the pixel on the crack, feedback, we can determine the width with a resolution that depends on the pixel pitch space. This is an optoacoustic sensor. So basically, the idea is to have a Fabry-Perot interferometer that we realize by using a silicon micromachining technique that is interrogated by using a continuous laser source, and the optical power reflected from the cavity is measured by using a photodiode. When an acoustic pressure hits this membrane, here, we have a deflection of the membrane. So the optical power reflected from the cavity is modulated by this acoustic pressure. So we have a direct transaction between the acoustic pressure, so the ultrasound wave, and the optical power reflected from the cavity that is measured by using a photodiode. To realize this kind of measurement, we use several components, in particular laser source and optical switch, because we use several sensors, and an electronic readout to generate and detect the signal. We have integrated all these components in just a single package here on the left. Here we can see the 3D design to be integrated easily on the drone. And on the right, we can see the first prototype. All the components are integrated in a single PCB board with a package size of 17 × 10 square centimeter. We have successfully tested this electronic with the optoacoustic sensors that we realize in our clean room, in our facility in Bologna, in several samples in our lab. Here, for example, we can see the prototype where there is inside this package, we have all the electronics needed for the measurement. Here we can see the optoacoustic sensors mounted on a Fabry-Perot connector. And then for the project, we also to realize some contact measurement, some acceleration measurement. Basically, the idea is the drone go in contact with the concrete surface and attach a vibration module to take acceleration measurement in a 3-axis acceleration. To realize this was necessary to design a system that was really small and really light to be attached by using an epoxy glue, for example. We decided to use this 3-axis accelerometer from Analog Device because it has a really ultra low noise densities, just 20 micro-G per square hertz. It's EDXL 355 from Analog Device with a 20-bit analog to digital converter and a bandwidth of 1 kilohertz, sufficient for this kind of application. We use this 3-axis accelerometer together with the transceiver from Texas Instruments, the CC1310. This transceiver here has an integrated 48 MHz microcontroller. It's perfect for this kind of application because we want to reduce as much as possible the power consumption. For this, we use sub-gigahertz communication. So we want to have this 3-axis accelerometer that we can take the measurement and wireless communication. So here we can see the design of the vibration module. On the left, we have a circular shape with a diameter of 15 millimeter and an height of just 20 millimeter, considering also the package. The space is mainly occupied from the battery because it was really important to increase as much as possible the battery life. We have designed the layout of the antenna directly on the top board. Is an helical antenna with the 668 MHz communication, and we have successfully tested the communication up to 100 meters. And the power consumption, as I was saying before, is of this kind of system is really low. We have 48 hours with a continuous transmission. Instead, we can increase a lot the battery life if we stop the continuous transmission and we transmit just every time when there is a really important signal to transmit. We can follow the presentation going with the vision part with my colleague Rafael.
Yeah, hi. Can you hear and see me? Can you hear
yes,
me? Okay, perfect.
Yes, of
perfect.
course, Rafael. Yeah.
All right. I'm Raphael from the Technical University of Graz, and I'll give you a short overview of the photogrammetric computer vision system that we are developing. Next slide, please. So our system consists of the following three separate components: a stereo sensor for capturing and storing the images, a software to process the captured images and generate depth data on a separate system, and finally, a web-based viewer where the user can view the generated 3D model. I'll go a bit more into detail on these parts in the next slide. Next slide, please. So for the stereo sensor, we have developed a custom design to fit the resist requirements. It consists of two high-resolution industrial cameras recording images at 12 megapixels and a small onboard computer, which is responsible for synchronizing and storing those images. Depicted here on the right, we have the 3D design, and on the right side, we have the assembled hardware sensor. Next slide, please. Secondly, we have the software responsible for generating 3D data. So this takes the captured images and input and generates corresponding depth data, as can be seen in this image. On the left side, we have the original input image, and on the right, we have the underlying depth map, where the colors correspond to depth. Blue corresponds to farther away points, and we can see this very well here since the concrete wall is slightly tilted. For the depth map generation, we developed a separate software pipeline, which utilizes machine learning for fast and accurate calculations. Since the computational load for this software pipeline is very heavy, we will have to run this on an external PC in the field using a combination of laptop and external GPU. The image shown here is created with this software, and we can observe how the small circled discontinuities in depth are reconstructed. Next slide, please. And finally, to present our results to the user, we have a web-based point cloud viewer that presents this 3D model. This should give the user an overview of the observed structure, and detected damages can be directly added to the model. Additionally, in this viewer, the user can rotate the model, inspect it, measure some angles and some distances, and generally get an overview of what's happening to the observed structure. And this already concludes my short overview presentation. Thank you.
Okay, this is Ramesh. I'm going to give you a very quick overview of what we're doing with the input from the 3D reconstruction and the stereo images. And so we've been working on a cognitive computer vision system. Can you go next slide, please? So the main idea in our design is actually that we are actually using sort of a human-like architecture for cognitive vision. So the main idea is that you have multiple different sources of information in any input data. For example, in this particular architecture, you see that the stereo image data is actually passed through what Raphael talked about to get a 3D depth estimates. And then you can analyze, obviously, the geometry in parallel to understand in geometry, can you identify defects? That's one part. Then the other part, which is complementary, essentially is machine learning based, deep learning based classification based on the appearance, which essentially we have actually extended since the Aerobe project to include more new things. And the idea is that you want to be able to focus on material defects and appearance-based effects. Whereas there is the third angle, which is you may all know that deep learning and modern machine learning is very data hungry. It requires lots of data. And then you can build good models of defects and so on. But unfortunately, it requires annotation. It's a challenge to collect a lot of data. So the standard classical way of computer vision and robotics, model-based robotics, was to really have models of the world and then use those models to tell you what should be the algorithms for processing. So we've actually developed what's called a topological feature extraction system that allows you to directly classify based on models of the world and the nature of the geometric distortions that you have in a crack to be able to come up with hypotheses. And then the last part is that you normally have high texture and also business in the image, which could be quite complicated in the real world. And then you can still use some notion of what each instance looks like and what regularity happens in each instance to be able to come up with context-sensitive anomalies. So these are like parallel guesses, just like a human would guess. It's like intuition subsystems in a human. which essentially guess at the core of what you think is an anomaly. And then you can fuse them together through coherence. And then you can actually then measure the properties of actually the cracks or defects and so on. That's the basic idea. So we had a lot of work done in Aerobe. Next slide, please. We extended this work. So effectively, we have a holistic engineering methodology for design. We use that, and then we actually now in Resist, things have changed in the sense that we have multi-camera data and stereo data here. So that means that we have direct estimation of depth from GRATS. And then we use our model-based approaches and data-driven approaches to do essentially both the ability to deal with small sample cases as well as large data sample cases. We have a simulation tool that allows you to evaluate these things without data to get an idea of how the tools work. And we have extended that. And we have optimized computational speed and robustness of our data analysis pipeline. And we actually have, in this particular presentation, another example of how we could, given the COVID situation, we had to go with simulated data and then test out alternatives for deep learning using multi-unit, what's called multi-unit for multitask learning, which essentially, again, leverages the same methodology to improve the performance. And finally, we have the 3D data analysis and mensuration, which is different from the previous Aerobe system, along with uncertainty quantification. Next slide, please. So just to, I don't want to spend too much time with these slides because time is of the essence. Just to give you an idea of what we were doing before. So in the top left of the image, you see essentially the image is taken in the Stromonas bridge from the last trial in the Aerobe project. And you can see the topology-based algorithm extracting potential hypotheses of where cracks could be. This particular image was processed downsampled in the previous case. And as a result of downsampling, because of computational speed, we were missing some key features, although we still be able to mark the cracks and so on. So we've improved the crack detection algorithm to be much more faster in speed. And we have actually applied them to also steel cases. And then you can see that it is transferred the whole Aerobe results to Resist without much issues, except for the optimization on computational speed. Next slide, please. Similarly, the deep learning pipeline, which was designed in Aerobe, was combined with this new system. Unfortunately, this slide, you cannot see this thing very well, but you can see that the deep learning gives you lots of hypotheses based on learning from large amount of data. And the topology extractor gives you essentially hypotheses as well. And you can combine them together to get reduction. Next slide, please. There are actually in the Aerobe system, we also have other defects types like spallation and bleaching, calcium leaching, and so on. We extended that work, the deep learning work, to include what's called multitask learning. The idea is that whenever you can actually design architectures where you can leverage the commonality between multiple tasks, and you can actually, in this particular problem, we know that geometry is actually the core issue for us, and the minute changes in geometry is what you want to label as actually defects. So therefore, we developed an alternative technique and tested it on simulations and validated them, and what's called a multi-unit technology. Next, please. And we extended our simulator to generate lots of data. We tested them, used that to train our models, and then check how well the simulation can transfer to real data. Next, please. And we can directly process from Rafael's data, we can directly process actually the 3D data and then look for, again, cracks, which are basically directly on the geometry information. So this is the parallel pipeline that produces an alternative hypothesis. And this is also finished. Next, please. And we have tested the integration between us and GRATS so far, at least in a lab setting. Because of the COVID situation, we're still awaiting more data from the actual drone and also the specific stereo data. Next, please. And this just shows you the final system and the integrated tool. So in a sense, what we have done is that we have actually extended Aerobee results, and then we have actually hardened the tools and optimized the tools and added very specific methods for addressing the resist requirements. Next, please. So that's basically the summary here. So there is one more piece of work which is not presented here, which is the idea of, because we're dealing with steel bridges and tunnels, and we didn't deal with steel bridges in Aerobee. So we are actually basically have built a color classification and defect classification techniques. This is in work already. And we are, one of the things that I would like to get some feedback from the end user is if it's possible to get some data sets with annotations, especially for the steel defects, because this is something which is a critical thing for us. And I hope that we can get support from you on this topic. Next, please. That's it.
Thank you so much, Rafael. Sorry that I'm not announced you in advance. Luca and Ramesh. Ramesh, I saw that you actually advanced a lot from the Aerobee work, because it was, I remember results of Aerobee, it was impressive, but right now you are moving on the right tracks, as I see. So we saw actually techniques for collection of data, techniques for sensing and processing of what we collected. Right now, I would like to return as a screened microphone to Kostas, who will talk about mobility continuity in the case of extreme event. Kostas, are you with us?
I am.
Wonderful, great. So your screen, your microphone, please.
Right, so we've heard quite a lot about bridges and tunnels and about drones in bridges and tunnels and sensors in tunnels and bridges. Now I would like to talk about the drivers a bit, with the people that are directly affected by in a case of extreme event. Mobility continuity system that we're developing in Resist, what essentially is a way for the end users and the managers of the infrastructure to be able to directly contact the drivers on a highway. So we're designing a system that has appropriate interfaces to enable the data exchange between the modules of the integrated platform that's internally in Resist. It should deploy a multimodal collaborative decision-making tool that will provide personalized rerouting advice to the user, wherever that is possible, to identify and integrate traffic simulation software that are internally developed from ICCS, explore the possibility of collecting information regarding other modes of transport. That goes to the multimodality. That's something that we are trying to do right now, and we are in a very good, very good level. Develop a model of highway users behavior under stress, a system that is developed by Ben Guriat, and I will very shortly talk about, because I'm going to say things that I shouldn't say because it's a bit over my head, and design and develop an interface tool that will collect real-time and on-scene information from social media tools, an innovation that we are very happy with, and I will talk about a bit later on. So the mobility continuity for passenger freight as a flow is it collects traffic data and vehicle trip data and goes through a road simulator, and it actually gives a new route to a driver. In case a structure has been closed, then a notification will go to the mobile application that every driver that the driver is carrying, the Resist application, and he will see that what happened, what was the event, and that he should change his route and go through another road, and actually will give you information on how long it will take and how much more distance he will have to take. Additionally, in later on, we will be able to provide information, especially when he's towards nearer to the start of his trip, to give suggestions that for different modes of transportation, mainly talking about public transportation. We are creating a simulation, a traffic simulator as well, called Sumo, based on Sumo, where the end users will be able to run simulations or their selected reroutes to see in any given time according to specific information like traffic information, the mixture of heavy and light vehicles, what kind of impact would have a reroute, a damage on the traffic of that road. Additionally, we will be able to give that the same system to the risk analysis in order to run simulations as well and see what the risk impact is. The Resist mobile application is based on the OpenTrip Planner for Android. I wish I could have a video. Unfortunately, my situation right now does not allow to play the video. The trip planning, these are the main screens. It's got a very comprehensive questionnaire during registration that is being used by the behavioral model in order to be able to gather the demographic data they need in order to make their behavioral analysis that will lead to suggestions towards the end user for more personalized dissemination information and giving not personalized but behavior appropriate messages for the road signs. On the third picture, you can see how the reroute is, the recommended routes are coming, and then you can see that there is a hazard in route and that the road is closed, and then directions for the new route. This is the back office of the application, and by back office we're talking about the screens that the end user is seeing. You can see that there is a red bridge on the left side picture. That bridge is an interactive control. Whenever something happens and the end user decides that he needs to close that structure, he just presses on the structure and then the reroute protocol takes effect, and then the reroute information goes to the mobile applications of the users. We gave the possibility of closing some kind of landslide that doesn't close completely the structure, but only a lane or part of the road. So we gave that possibility as well. Can you hear me? Because I'm getting my connection is unstable.
Yes, we can hear you right
okay,
now.
all right. We have uploaded our Resist application on the Google Store, on the beta version of the Google Store. This is the link for anybody that is interested. He can just download. It's like a few megabytes and play with it a bit. And if you can register as well, you can get demographic data view. And then we have the sentiment analysis. The sentiment analysis is based on a system that we would like to gather information from social media. We're mainly focusing on Twitter just because it's more live than other systems, other social media like Facebook or Instagram, and it's more text-based, so it's easier to be able to collect text from there. We create a data set which we then we annotate, and we feed it on a neural network model in order to get specific emotions, in order to see what is the emotion of the user of the road. That can be then used with the system from Ben Gurion in order to give better personalized information back to the user. The emotion detection happens, as I said, is based on sentiment analysis, but it's a natural language processor that has linguistic characteristics of social media posts. It's a fully annotated data set over the PUT68 basic emotions. And as I said, I'm not going to go too far into it, but we pass it through a neural network, and then we get an emotion on the person that has tweeted something about the event. That might be anger, fear, joy, stress, etc. We obviously have some challenges with this data. The content is dynamic. There's multiple participants from heterogeneous sources. There is a huge amount of text. There is not all input is accurate. Some of it is just noise or it's just malicious. Internet internet language is not exactly your standard language. So we have non-standard or incorrect spelling. We have limited set of features for automatic clustering and classification. As I said, informal nature and loose syntax. And there is a choice between there, they are there, and there that is hard for an IT system to categorize. And there is a redundancy due to retweeting, reposting, and so we can capture the same the tweet, then the retweet, and then the repost, and having the same message coming out over and over again, creating bias. But we do add emojis and symbols in our neural network in order to be able to read those as well, which is part of the innovation. Our work, the work in progress, because this is a work in progress, is supposed to finish in a few months from now. We are doing an evaluation of the traffic control center data set because we would like to get information straight from the traffic control, especially if when they have traffic control data related to the traffic and the mixture of heavy and light vehicles at any point on the road. And that would cause like a higher automation of the system. And evaluation and assessment of simulation execution times based on the simplified test case. The thing with the traffic simulations is the more parameters you put, the more intensive they become in terms of processing power and time. And we want to keep a realistic balance on the two, not taking hours in order to produce a simulation is one of our goals. Development of complex test cases simulation scenarios. We have started running some simulation scenarios in the context of the risk management system, and actually we validate them, not exactly validate them, but we cross-reference them to the Google system, and they seem to be quite accurate. Enhancement with multi-modal rerouting. Right now, we are able to give suggestions when it comes to buses because they are run on a very, very fixed schedule. In order to add airplanes, maybe naval, like ships or boats, then we need to interconnect with the APIs of the companies, which is much more challenging. Some GUI enhancement, as you've seen from the pictures, we are trying to keep it familiar, like everybody's using Google Maps, so we're trying to give it a Google Map feel, but we are doing some enhancements on the GUI. To analyze the data flow for the collection and processing of the data collected from the social media APIs. Most of our works right now is on the sentiment analysis. Continue the collection of the available research work on the field of sentiment analysis. Of course, being in Europe, GDPR is a major concern for us because we are dealing with personal information. So we are applying comprehensive consent forms before giving any kind of personal data in order to be able to be covered from that, and initiate the user registration for the mobile app, something we actually have done already, so we can get some demographic data. That's about it from me. Any questions? I'm guessing we're gonna handle in the Q&A.
Yeah, I'm collecting some questions actually through the different channels. I have also comments from Elit Oppenheim from Ben Gurion University that wrote that please pay attention that end user means control station operator and row users are the drivers.
Correct.
One of the slides.
Correct. It's a very good. Thank you very much.
Yeah. Okay. Wonderful. So I would like to pass a word to a civil engineer, Dr. Marta Frantistow, who will give a presentation about resist attitude to vulnerability assessment and risk management. Right now, we are going to the civil engineer section. So it's amazing.
Okay.
So,
thank you,
Marta.
Edward. I will briefly describe the risk assessment and management part of the RESIST project. I do not see my presentation.
Just a second, I will try to share it. And once you need me to go forward, please tell me to do it.
Okay, I see
Yes.
it.
Like next slide, please.
Okay, I will, okay, so it's risk assessment and management in the RESIST project. I will skip some slides to speed up the process. Okay. How come I can't skip the slide?
No, I will do it for you. Please tell me
Oh,
to do it.
okay. Can you go to the next slide?
Mhm.
Okay. Here are the hazards under study: earthquakes, explosions, fires, landslides, scouring of the riverbed, cyber attacks, and all of these together with adverse climatic conditions that accelerate material degradation. Can we go to the next? Okay. So what we have done was to develop material degradation models that predict material damage as a function of time. And then we performed several structural analyses at several points in time to get a curve like the one that you have in front of us, so that you can see that the same loading at a later time can produce more damage and a higher probability of failure because of material damage. Well, this is a very useful curve because it tells us when to intervene, which is when the probability of failure becomes unacceptably high. Can we go to the next? Okay, so here are the steps in the risk analysis for the hazard of interest and the structure of interest. You do a structural analysis that will determine damage, and then based on damage, you determine loss of functionality, and based on damage and loss of functionality, you determine consequences that you see, fatalities and injuries, environmental cost, and economic cost. Go to the next. Okay, let me tell you how we determine loss of functionality. You start with a structural analysis with a loading of interest, and you determine damage. Then you go back to the structural model, which you modify. No, Edward, I still need, which you modify it in order to include the damage. And then you load this model with a mix of vehicles, emergency vehicles, passenger cars that are of interest in order to see if the damaged structure can support it. Now, if we can go to the next, some examples. This is the tunnel in Italy that will be one of our pilots. The assumption is that it was under fire, and you see the bending moments here in red and blue in all of the points that you see here. Now, these bending moments have been linked to damaged categories, as you will see in the next slide. Okay, there are damaged categories, collapse, light damage, and so forth, that are linked to rehabilitation techniques that you will see in the next slide. Edward? Okay, so you see the link between damage categories and rehabilitation techniques, and this is also linked to cost and duration, and it is also linked to environmental cost, as you can see in the next slides. Edward, can keep going? Next slide. Here, you can see that rehabilitation techniques are linked to environmental cost. So next slide. Next slide. Okay. Some of our results. This is the bridge in northern Greece that will be one of the pilot. The assumption is that there was an explosion near the eastern abutment or an extreme earthquake that produced settlement of the abutment. That was a settlement of 117 centimeters that transformed the eastern beam into a cantilever. To fix it, we have assumed external pre-stressing of the eastern beam and part of the adjacent beam, reconstruction of the abutment with a stabilization of its foundations, and jacking of the end of the cantilevered beam. All these at a cost of 2,100,000 euros, while the bridge will be closed for 12 months. Now in the next slide, we can see some of the consequences that have been monitorized, and you can see the reconstruction cost, the cost of the local traffic safety measures, and the loss of revenue because the bridge is out of service. These are the direct costs. In the area of indirect costs, you can see fatalities and injuries, damaged vehicles, and travel delay cost to the road users due to detours. Now, you can see here that the indirect cost can be far more significant than the direct cost, and you can also see that the duration of closure is very important, which gets me to my next slide. Here the assumption is that immediately after the extreme event, the drone was sent to do the inspection, and you have heard the description of this drone. This drone collects all the measurements that civil engineers need for structural assessment, and these measurements go to integrated civil engineering software. So based on all this, we have assumed that we can speed up pre-construction time by 20 days. And here is the impact of this. You can see that there are savings of more than $500,000 in direct costs, primarily because the bridge was out of service for a smaller period of time. And there are savings of more than 125 million. This is indirect cost, primarily because travel delay cost to users due to detours was decreased. Now, if we can go to the next slide, what are the achievements? I think that the achievements are that there is a detailed and credible structural assessment that permits actionable decisions. Also, there is a credible and actionable assessment of loss of functionality so that the officers know what is the mix of vehicles that can safely use the damaged bridge. And also, there is a combined assessment of structural resilience and environmental costs. Now, what are the challenges that we see in the next slide? The challenges are that it's very difficult to quantify some of the consequences, and specifically, it is difficult to quantify the linkage between structural damage and fatalities or injuries, or fires in tunnels and fatalities, or high pressures because of explosion and fatalities. Thank you. Thank you, Edward.
Thank you, Marta. Thank you a lot. It was quite interesting to learn about money, about how much can we save in direct and indirect costs from the implementation, possible implementation of results of RESIST. And thank you a lot one more time. Right now we are moving to the interesting part session of this webinar. It is a discussion. Right now, I would like to ask participants who would like to participate in the discussion. I can promote you and open cameras and microphones. If you would like to talk and to ask live, so please raise your hand and I will promote you to the panel. So it will take a few minutes. Meanwhile, I have a question that arrived by email. It is a question to Karen, are you with us, and to Marta, maybe. The question is about maybe you are familiar with methods, materials, standards, or any methodologies that can help quantify indirect environmental costs and or maybe to implement some solutions in order to improve the capabilities of road operators to meet climate change challenges. Maybe it is two questions actually about the methods of quantifying indirect costs and environmental costs, and the second one about the solutions that can help to improve capabilities of road operators to meet climate challenges. Yeah, please.
And Edward, can you tell me who that was directed to again?
It is directed to you, Karen, as a head of Transportation Institute, and also to Marta, because Marta used some quantifying methods of indirect costs and environmental costs.
Right. There are some resources that have been published by the Transportation Research Board, which you are likely all familiar with, and I can certainly send links to those reports. But when we talk, I'm writing myself a note, but when we talk about the indirect cost, it's multiple. So it's everything from health, from higher costs of medical use and of appointments because you're located in a place that has high levels of poor air quality, high levels of greenhouse gas emissions. I'm afraid I didn't hear the entire question, Edward. So if you could put it in the chat or repeat it, I would appreciate it. But I think I got the gist, which was quantifying the indirect costs of different greenhouse gas emissions and other factors. And so I would be happy to send some resources to you to distribute to this group that talks about this more in depth.
Yeah, and the second question is about solutions, or maybe methods or technologies can to improve capabilities of road operators to meet climate change challenges. It's a little bit general question, but if you can address or maybe explain a little bit.
Let me punt that to Mata right now, and then I will respond following her.
Great, thank you very much. Mata, would you like
How
to?
you can quantify environmental costs? Is this the question?
Yeah, maybe a sample of some method or what you use to quantify.
Okay, specifically in the RESIST project, I was using the result of a previous project that we had. The project was SenseKIN, and the goal of this project is to assess the environmental cost in construction and to quantify the impact of these costs. The work was by the University of Stuttgart, and in RESIST, I just used the results.
Okay, okay, thanks a lot. As the next question is to Dr. Luca.
Yeah.
Yeah, and the question is, do you have a plan to minimize the weight of sensor of your system?
Sorry, can you repeat, please?
Do you plan to minimize the weight of sensors of your system?
Of course. Yes, so at the moment, the problem for the weight is just for the crack width system, because instead for the depth and for the vibration modules, the system are really small and light. So we are now to discover if the crack width system, that is the bigger one and the heavy, will be integrated on the factory. If we have some problem on that, we are anyway in parallel working on some second source solution where we are not going to use some optoacoustic sensors where we have to use a laser or other component. We use a different principle, maybe piezoresistive sensors that in contact with the concrete, we have a signal more or less in the same way, or some optical solution, like for example, a range meter with a lens to improve the resolution, and that will be used like a mechanical profilometer, so to detect the width of the crack.
Okay, thank you a lot. The next question is to University of Seville and Father Katek, Miguel and Guillermo, please. Actually, the question is about what are the limitations, current limitations of UAV system still actual for bridge inspection, like in time, weight, any other limitations, battery life?
Well, I think that the very strong limitation with the aerial robots is the battery time. So actually, I would say that the battery time would be around 15-20 minutes. So we have to take this into account in the planning of all the things. In fact, we took this into account in the design, because when we decided to have a different aerial robot for different purposes, because every 20 minutes we will have to land and change the batteries. So it is also a good solution to separate in different drones that are much more flexible system. But I think that this would be the main limitation, and also the size. So if you are flying inside below bridges, but also inside tunnels, so it's so the size, the overall size of the the robot, it's also limits the areas of the bridge that we can reach, even if we can fly with enough safety inside tunnels.
Okay, thank you. And actually, the last questions that I have so far, maybe somebody from the participants will add. It is a question from our chief tunnel scientist, Avi Bachal, who asked, why should we use drone for inspection and not just use a ground vehicle? It's actually also a question to all the team of Resist, maybe also to Miguel and Guillermo. Costas?
Well, I think that Miguel and Guillermo would be more suitable to answer, but the one that I would say is Rich. A tunnel might be something like small, but there is tunnels that are like what, 8 meters high, 10 meters high. If you're using a ground robot and you want to check stuff that are in the ceiling or on the curve of the tunnel, a ground robot would be quite challenging to do.
Okay.
Yeah, I think that this is the main. So if you have a bridge that is 80 meters tall, it's not possible to inspect it with a ground robot. Inside tunnels, it will be possible, but also so the aerial robots has the advantages of the very fast fast displacement between one point and another, so it is more flexible in this sense.
I also have something to say here. We had a project, RoboSpect, that involved ground robots for tunnel assessment, for tunnel inspection. And there were several problems. One of these was, it was very heavy. And when we tried to use it in London Underground, it was very difficult to get it there. It was big and heavy. Things are much easier with a drone.
Okay. I think this is a quite good question and answers. I also have a question from Karin. It write down on chat to all the panelists. Karin, should we answer it right now, right?
Sure, if you have a moment. This is a very big
yes.
for the resilience of our systems here.
Yeah, of course. This is a question to all the panelists. Does anyone have insight on the use of drone for suicide and the trespasser reduction? Costas, Marta, Guillermo?
Can you repeat, please? Use of drone for suicide?
Suicide and trespasser reduction.
Well, without having something concrete, I know of a group in Japan that are checking remote areas with drones in order to see for stranglers or people that might are looking for self-harm. But for trespasser reduction, there are several projects that in the logistics sector where they are using and security/logistics sector that they're using drones in order to check the larger containers area for trespassers and any kind of security issues.
Okay. Somebody else would like to address? Ramesh?
Yeah, I know that in the area of security, at least for intrusion and so on, there are actually companies doing drone-based inspection. In Siemens, for example, we were already doing these type of things with for oil fields and stuff like that. So yeah, that's I don't know about suicide detection because that is quite specific. In terms of what you need to do for that, in terms of behavior analysis. But there are companies, obviously, with onboard drone video analytics that actually detect people and so on. So effectively, there are techniques for at least knowing if somebody's intruding.
Thank you, Ramesh.
Actually, for example, we did some projects regarding that, regarding trespassing and locating people that are trespassing, sorry, and following these people and so on, yeah, and communicating the position of these people. So yeah, that's a more, let's say, common topic than the. I never heard about the suicide. I really don't know. Maybe if you can put an example about how that can be prevented. I really don't know right now. I never heard of that. Maybe an example would be.
Okay, wonderful. Thanks a lot. We have new question on the chat from somebody who called EB. What are the requirements and specifications from the sensors and the models in order to validate detections, for example, the cracks, or the also of the method used as secondary and alert systems?
I can take up at least the part which involves the vision sensor, and so you know the way we obviously the the performance of the detection systems depend on the resolution at which you acquire the data. And then also, of course, the photogrammetry system has its own limitation on what kind of depth accuracy you can get and uncertainty in the depth. So therefore, in the Aerobe project, what we did was we actually assumed a planar surface that we were inspecting, and then we had a particular distance for acquisition, and we designed our camera sensor to basically get a certain minimum resolution for the crack. So in that sense, the global requirement of the crack width estimation mapped back to the sensor requirement for the resolution and the distance from which you acquire. And then the other requirement that you have for the basically is one is the resolution requirement. The other requirement that you have essentially is the false alarm and detection rate requirement. So ideally, you would like to have almost all things detected, which are real cracks, and then you would like to get zero false alarm, but this is impossible. So that is the reason why we have a multi-pronged strategy where we actually have hypothesis generators that actually generate hypotheses basically of different degrees of certitude, and then combine them. So the way we essentially, in the end user will have to use it is essentially by deciding on some trade-off on how much you want to basically guarantee detection and how many false alarm you're willing to accept. So that's actually an end user parameter typically. And in our system, we have the flexibility to decide what that would be. But also another thing, which is also a way of reducing this type of time to look at things, is by using already specific domain knowledge, like knowledge about where, which parts of the bridge structures and which parts of the tunnel structures you want absolutely to be able to be highly sensitive to. So therefore, that information can be fed in to be able to reduce the system. So in other words, it is the systems have been designed in a way that these elements are transparent, and the human-machine integration parts can then be taken into account according to the user context.
So instead for the contact sensors, the specification are for the crack width measurement, we have a resolution and accuracy of 0.1 millimeter for the crack width system. Instead, for the crack depth measurement, the accuracy depends on the depth itself. More or less is 5% of the depth that is measured. Instead, for the acceleration, for the vibration measure, it depends on the bandwidth. We have sub-milli-G resolution.
Well, you're muted.
Sorry, yes, of course. Thank you very much. And using this opportunity that we are a few minutes after the schedule, I would like to pass a word to Kostas to sum up our meeting.
Well, not so much of a sum up. I would just try to. Before that, on your first question, I think one part of the question was if there is any techniques to reduce emissions, etc. And I want just to know, just to tell people that are in IT to check the green IoT techniques that are very in trend right now. It covers both IT and both software and hardware, and there are some very exciting research opportunities over there with some very nice results. You're going to be hearing about it more and more as the need for less energy and less pollution comes up, and it seems that of course it's more obvious that materials would cause pollution and emissions, but IT is so evolved right now that is one of the major factors in pollution, and there are many actions taken right now in order to reduce that. Green IoT, very interesting. So what I want to say, we try to present our system. Our system is very extensive, so most likely 2 and 3 or 4 hours will not be enough. I would like to ask everybody to sign up in our newsletter and get all the news of, as you heard, the very exciting innovations that we're trying to produce in our project. We will be holding more webinars, and I will be holding we'll be out disseminating more information, and everybody's of course willing to contact me or any other of the partners for extra information. And once again, thank you to Dr. Philbrick for staying up all night in order to join our webinar.
Yeah. Thank you a lot. I really appreciate your time and efforts, and happy to meet all the team together. Not all the team, but the most of the team of Resist together, talking about the project. And also, I see right now that some connections are established. So I suppose
success.
Yeah, you will have a data. I remember Robbie struggled with data lock, and this is the main question also for you. Thank you a lot for all the participants. Just a second, last. Okay. So, and of course, Angelica shared with us Media Center of Resist project. You are welcome to visit website and follow us. Also, deliverables are published there, and newsletters, events, and so on. Thank you a lot for time. If you have any further questions, please do not hesitate. Send me or call me, or also you can call to the Kostas or any other project team member. And thanks a lot. Have a nice day, or maybe have a wonderful morning to somebody who is early morning right now, and stay safe.